The next contribution comes from the Hong Kong University of Science and Technology. It's going to be delivered by Professor Teng, and it's entitled AI-Driven Integrated Material and Process Design Toward a Sustainable Future. The floor is yours.
So thank you, Mariano, for the kind introduction. My name is Zhou. I'm an assistant professor in the Sustainable Energy and the Environmental Thrust at the Hong Kong University of Science and Technology, Guangzhou. Today I would like to show some of the work that we have done in the area of AI-driven material and process design for sustainable energy and the environment. So this is my self-introduction. I got my bachelor and master's degree for chemical engineering from Nanjing Technical University and also ECAST. And I finished my PhD in 2016. Yeah, 2016 with Professor Kai Sun Maha. And then I have some experience as a junior professor and in Magdeburg, out from Greek University in Magdeburg. I also visited Professor Prof. In 2017 during my postdoc time, and then I am assistant professor at HKUST Guangzhou. So I would like to firstly to briefly highlight the research background and the research strategy, and then I would like to introduce the method for computer-aided material and process design. And I would like to give you some examples. Maybe I do not have time to introduce all the examples, but I will highlight briefly. First one is solvent design for CO2 capture, and second one is extractor design for gas-solid desulfonization. Then it's a phase-change material design for solar energy storage. Finally, I would like to introduce the recent work on porous material design for hydrogen storage and gas separation. So, if we look at the whole, let's say, sustainable energy generation, energy storage, and then emission reduction, all these different sectors, you will see that we have a very important factor, design factor. Here we call it functional material. So functional material are key to achieve sustainable energy and environment. For example, if for energy storage, you may use phase-change material. For thermal storage, you may use perovskite or moth to store hydrogen or methane. For energy conversion, you may use a catalyst. For emission reduction, you have to use somehow like a solvent or adsorbents to get rid of the undesirable emissions. So, but we are chemical engineering, not a chemistry. Okay, so then our task is not only to design the new materials, but also to design new process technology. So my research focus is computer-aided material and process design, briefly CAMPD, for sustainable energy and environmental applications. So the method for CAMPD, how to design material and process simultaneously. If we look at the molecular or material discovery method, basically you have three different kinds of methods. The first one is experimental chemists. They do a lot of experiments. If you are lucky, then you may find your best molecule or best material, but then you have to spend a lot of time. And the second one is called computational scientists. They use high-throughput computational screening methods. For example, they use DFT calculation or molecular dynamics. They can also predict some properties. As PSE or process systems engineering, we use the third method, which I call data or systems engineering method. You firstly build a mathematical model to predict the property based on the structure of your chemicals. Then, with this kind of structure-based property prediction model, you can do optimization. Then you can find your best or desirable molecules with a few iterations, or a gradient-based, or even other different kind of optimization algorithm. So, the first step for molecular design is you have to express your molecule in a way that the computer can recognize. So this is called molecular encoding. Basically, you express your molecular structure into a mathematical descriptor. Of course, you have many different methods. You can express your molecule as a slice string. Then you can do one called encoding. You go to RNN or CNN. You can also use the graph methods or graph theory. Then you use GNN or GCN. You can also get your molecular descriptor. Finally, also the simplest method, it's a group contribution method. You simply just use the group numbers. Okay, so these are the different methods to express the molecule with mathematical descriptors. Okay, in computer science, they also call features. So if I use this as an example, basically you have your molecular structure space. Then you use a property model, you predict your molecular property, then you can do optimization. So this is basically the way that we do in CA&D, computer-aided molecular design. Let me give you a very simple example. If I give you this kind of a set of molecular building blocks, I want you to design a molecule with, let's say, with a minimal viscosity toxicity. You can build a structure-based property model with structural feasibility constraints or structural complexity constraints. Then you can get your best molecule. Okay, and this one is optimal. It's 1,2,0,0,1,0,0,0. This is nothing but isopropanol. So this is how a computer can help you to find the best molecule. So, but as I just said in the beginning, we are chemical engineering, not chemistry. So our task is to design a best process where the molecule plays significant role in the process. So then, in a word, functional molecule or material serve the process. They must be simultaneously designed together with the process. So the task is computer-aided, not only computer-aided material design, but computer-aided molecular or material and process design. What is the, if I give you a simple vision of a multi-scale vision on the CO2 capture, because later we will introduce the CO2 capture as an example. We have material here, and basically you have to design the structure and the composition. Sometimes you can use composite material or blend solvent. Then you also need to find the best composition. Then you go to the phase level, you predict the thermodynamic or transport properties. Then you substitute those properties into the process models. For example, then here you have to also to design the process variables. For example, the sizing, the operating conditions. So these are molecular or material variables. These are property process variables. You have to design both simultaneously because they have strong interaction. Okay, so this is the framework of CA&D. Now we want to design process. What do we do? You move the objective function here from molecular property to process performance, because this one is our final objective. So then, do not forget the process conditions as your process variables. You also have to carefully design the temperature or pressure, something like this. So then you can do optimization. You can formulate typically MI-NLP program. You can solve you get the best molecule. At the same time, you get the best process conditions. And of course, you have to use very good MI-NLP solver. So let me give you some examples. The first one is ionic liquid solvent design for CO2 capture. If I give you such a process where we have an absorber, we have a feed gas like the flue gas from power plant. Then you have a cooler, then you have absorber, then you have ionic liquid, let's say regenerator. You send ionic liquid back, you do the absorption again. This is your ion molecular building blocks. You have anion, you have a cation core, you have a substitute groups. And pay attention here, we have many CH3. We have NCH3, we have ANCH3, we have CICNCH3. They are different. NCH3 means this CH3 group are connected with the nitrogen atom on not aromatic, and this one is on aromatic ring. This one is on aliphatic cycle ring. So they are different groups. Okay. Then you have also to write different structure feasibility equation in order to make sure the molecule is structurally feasible. And this one is how we express this ionic liquid into let's say a group contribution way. Now we have this ion molecular structure, we have a property prediction model, we have a kinetic mass transfer coefficient, we have a CO2 equilibrium solubility, then we have also our operating conditions, finally we have our process performance. I can tell you, if you use traditional thermodynamic model, we tried before, we use PSRK, we use PSK plus UNIFAC, you cannot get it converge within 48 hours, because here we have a high pressure in the vapor phase, so you always have to use the EOS, equation of state. It may be very hard to converge. But what we do is we change this traditional thermodynamic model with the machine learning model. We change this with the machine learning model. What we do is we collect more than 10,000 experimental data. Then we predicted the solubility directly with neural network. This helps us to solve the problem very quickly, because then we can solve this kind of very complex integrated design program. We get the optimal ionic liquids like this, 2CH3 group, 2 NCH group 1, and you can find we have 2 isomers. Because we use group contribution method, we cannot distinguish between isomers. Okay, this you have no choice because you use GC method. Then you have to do post design. But fortunately, our process models tell us our annual cost. It's more than 10%, let's say less than the existing industry process for power plant CO2 capture. So this one is the first example. The second example I would like to show is phase change material design for solar energy storage. How can we design a best PCM to store solar heat? The idea is we have a thermal energy storage here, we have a sensible heat, we have a latent heat. So what we do is we want to design a phase change material. At the daytime, the phase change material gets melted. And then at the nighttime, it gets solidified. It will release heat. So at the daytime it's storing, at the nighttime it releases heat. So then the first idea of all the experimental scientists, they will say, okay, please select a phase change material with highest latent heat. What I can tell you, this is wrong. Why? Because when you have a high latent heat, you may also have a low thermal conductivity. You may also have a lower density. So you have to balance all the different properties. Okay? So then we give you a simple example. Here is like a hot water-driven thermal tank, where we pack the PCM material, a circle, bore PCM material inside of the tank. Then we formulate this kind of heat transfer program into a partial differential equation, basically. And then you solve this partial differential equation. We have, for water, we have a heat balance. For PCM, we have heat balance. We have initial condition, we have boundary condition, we have some other conditions. Then you will find the heat properties. We have 5 heat properties. The first one is melting point. Then we have a latent heat, we have a density, we have a heat capacity, we have a thermal conductivity. It's not only one heat, latent heat, we have 5 properties. Okay? Then again, you formulate your optimization problem, like you have a property model, then you have a process model, as I just listed here. These are process models. And then we have heat storage capacity. This is our objective function. What this tells you? This tells you how many heat you get stored divided by the time. Okay, it's like when you charge your battery, when you charge your cell phone, you also need to account the charging time, right? So we have this kind of objective function here, and then you can do optimization. Then we find our best PCM. Here you find the heat storage capacity is 30% increase compared to the industry one, which paraffin wax. So in Chinese it's Shila. Okay, so this one is widely used in industry, and you can find we have optimal trade-off or balance between 5 properties. This is not only 1 or 2 properties. You have 5 properties. Then, okay. So final example I would like to show you is what we did recently. We know that MOF meta-organic framework is very popular. It's a porous material. You can do a lot of application with this kind of material. Then we design this porous material for hydrogen storage and gas separation. Let me first show you this kind of material, a meta-organic framework. This is very important porous material for energy, many energy and environmental applications. You have organic linker, you have metanols. Yeah. So then we focus on hydrogen storage and hydrocarbon separations. We have two different applications. Okay, so we have age, we have vertex organics, we have vertex metal, we have topology, and this gives you a huge number of MOFs. So this is MOF structure diversity, and yeah, this also shows you how many different meta-organic work that already been synthesized. So the question is how to design it. So fortunately, we have material big data, so 就是说材料大数据。we published a paper on engineering journal. We summarized all the different material databases, and these are public. Okay, it's totally free. Yeah? You can find these different kind of material with different properties. You see, you have many different properties. If you have some basic computer science technology, you can just extract and do data mining from this kind of material database. Then you can get your database. So I call it material big data. Then we built such a machine learning-based material design framework, and we have a lot of different material. We have descriptors, we have data. Then we can do machine learning model. Here we have to do active learning because experimental do experiments is always time costly and also let's say expensive. You have to minimize the effort, experimental effort. And how can you minimize the experimental effort? You do some samples before, and then you do active learning. Okay, this is very popular in PSE area. So with this kind of framework, you do, and we built a machine learning model, which is a graph convolutional neural network for predicting the hydrogen adsorption uptake for different MOFs. What we do is we firstly decompose different MOFs into, we do structure decomposition. We get the metal, we get organic linker, we get the topology. We calculate some typical microscopic properties for different MOFs. Now you do the encoding. For metal nodes, we do it directly in embedding. For topology, it's also directly embedding. For geometry properties, also directly embedding because they have some certain, let's say, for metal nodes, you only have about 30 different metal nodes. For topology, I would say you have a 20 or 30 topology. But the difficult thing is organic linker. The organic linker is very complex, and in this case you cannot use group contribution method because for porous material the group contribution method will fail because they do not consider the connectivity. Okay, so now we developed a graph convolutional network GCN based method. Then we embed this MOF organic linker also into the chemical features, and we can use the neural network to predict the adsorption uptake. So then we use this machine learning model to predict the meta-organic framework for hydrogen storage. What we find is the best MOF we find has 47 gram per liter hydrogen adsorption capacity. This developable capacity is the adsorption capacity at 100 bar minus the adsorption capacity at 2 bar, because this one is charging, this one is discharge. Okay? So and the best experimental verified MOF has 42, so we have about 10% increase. So then a final example, which is also very interesting example, is how can we simultaneously design the material with the process. I give you this kind of figure where we have this multi-scale, let's say, vision. We have a material structure. We can use a machine learning-based property model to predict the property. Then we can use a magnetic process models to predict the final objective function. Then we can integrate material and process design. We also wrote a very nice review paper on this journal, and together with Rafi. We call it hybrid machine learning and magnetic modeling. We have two different types of models. Now, for this most again, we have material structure. Then we predict adsorption loading and heat of adsorption. Then we do process modeling. We have our adsorption process models. Okay, we have 2 minutes. And then later you can do optimization. Okay? So then the first thing is how to express morph in a way that the computer knows. So then descriptor. We find 5,000 descriptors. Then we do feature engineering. In computer science they call it feature engineering. And then we try to minimize, we find 90 descriptors are key descriptors. Then we use this 90 descriptors. And the interesting thing is, when I asked my colleague in the chemistry department, he told me that these descriptors are really, really important. So this is the magic of computation, right? And then we use this 90 descriptors to build a machine learning model, and then we directly predict the adsorption loading. Then we substitute this adsorption loading here into a pressure swing adsorption model. Then we can change an MINLP problem into an NLP problem because the molecule expressed in descriptors. Okay, then you have to solve NLP only. After you solve the NLP, what you get is you get the best descriptor value. The next step is to match the descriptors. How to match the descriptors? You decompose the morph into different building blocks. Then this is your morph descriptors. You can just express the distance between your descriptor and the optimal descriptor. Then you find your best morph. This best morph can save 20% of the total energy consumption on the pressure swing adsorption, industrial pressure swing adsorption, because we have this kind of, we also optimize 2 pressure level for operating times. We have pressurization, adsorption, rising, desorption. So we have 6 continuous variables. These are also optimized simultaneously with the descriptors. So summary, we did some interesting study on some examples. We try to find the key material, and also we take into account interaction between the material with the process operators. Okay, so we did some inquiries of a lot of things. So I would like to advertise my group at HKUST Guangzhou because I was fortunately selected as the head of the Max Planck Partner Group on carbon capture and utilization, and we will focus on material options, especially on solvent blends, phase change solvent, or morph composite material. We also will focus on absorption, adsorption, and hybrid separations. So maybe after 2 or 3 years, we will also focus integrate capture and conversion. And then right now I have I'm building my lab, and they are already there. So my group will do a lot of experiments to try to verify the design results. Okay, so that's all. Thank you very much for your attention. I want to apologize because I have to leave this afternoon, but I will come back tomorrow morning, the whole morning. If you have any question, you can write me email, or you can ask me tomorrow morning. And Rafik and the Professor Shi said he arranged that I can come to the stage to ask a question tomorrow morning. So sorry for that. Thank you.
Thank you very much.